let's get down to the subject matter today, which is space-time. Ever heard of space-time? Well, what we've been doing these last couple of weeks is doing a little review of geometry. And geometry is what general relativity, the owners of space-time, right, what they base their theory on. They base it on geometry. It's a geometric theory. It's known as a geometric theory. It's known as a geometric theory of gravity. So geometry plays an important role, and that's one of the reasons I went through this little series that went from point to line to circles and all the way up to toruses, okay? Because all of that is really like the foundation of general relativity. When you look at the people who created relativity, it wasn't just good old Einstein. You had other people there as well, and they all worked on this geometric, on the geometric context that underlay what we have today as general relativity. And so we have to start at geometry, no doubt about it. And here we go. Let me just do a quick review of what we did this month so that we can get it all into proper context. Point, what is a point? Well, this is what they show you. They illustrate a little dot. Could be 2D or 3D. Doesn't matter. Usually it's 2D because they just hit the chalk on the board and you're looking at it from a frontal. Yeah, it's got depth. The chalk has depth, but you're looking at frontally, so it's 2D for all practical purposes. But that's what they illustrate. Is that what a point is? Well, no, what a point is a location, and that's how they define it. That's how they describe it. And so there's nothing to illustrate for what a point really is. Okay? So the word point is very misleading because they show you a dot, but they mean location, and there's nothing to illustrate for location. And what they do is they use the dot to pictorially represent the location. That's what's happening here. The dot belongs to physics. The location, well, I don't know who that belongs to. It also belongs to physics, but these people quantify locations by saying that you need two coordinates to establish a location, or one. You know, it depends on whether you're doing linear, or you're doing planar, or three-dimensional locations. You know, and you have triplets, or you have ordered pairs or whatever, depending on what you're trying to do. But the point is that the location of mathematics is not a location. It's not a qualitative location. What it is a set of numbers that tells you where you are from some frame of reference. That's what a point is. Okay? And again, they never define it. They say it's primitive only because they're trying to mix physics, the dot, with the word location. What is a line? Well, a line is a bunch of locations. And so they say, well, it's one-dimensional. But that's not what they illustrate. What they illustrate is what you see there, an elongated rectangle, two-dimensional rectangle. So both the dot and the line are two-dimensional, what they put on the board or on the paper, because there is no way to illustrate anything below 2 dimensions or above 3. And so everything out there is either 2 or 3-dimensional, every object out there. There is no object that is 1 or 0-dimensional. There is no object that is 4-dimensional or above. Everything is 2 or 3-dimensional. And so they illustrate that line, and what do they mean? Well, they mean a bunch of locations. They say it's one-dimensional, and what they're really talking about is a bunch of locations. And it turns out the locations they say is 0-dimensional, and with a bunch of 0-dimensional locations, they form a one-dimensional line. You figure it out. Do many 0 dimensions form a one-dimensional line? That's what you got to ask yourself. It doesn't make sense. The language is wrong. The concept is wrong. It's wrong because, again, they're describing and defining mathematics, but they're illustrating physics. That's what's happening. Okay, what is a plane? Well, a plane, again, it shows something like that. That's one type of plane, just one among gazillions of planes that are out there. Why didn't I put an illustration? Well, I didn't put an illustration because they say that the plane is infinite. In other words, you never see the end. You can't see a plane, the definition, the description of the word plane, you can't see it from a bird's eye perspective. You don't see the edges of a plane because the plane, like the line, by the way, are alleged to be infinite, meaning it's still growing. We haven't finished constructing the plane or the line. And that's one of the conceptual problems with all of these, okay? They just say it's infinite, it stretches forever or extends forever. So we don't know what a plane is, not the mathematical plane. In physics, we know what a plane is. Plane has borders all around. It's got shape. It's an object, also known as a figure, synonym, okay? What is a solid? Well, again, I didn't draw it because it's a bunch of locations, and worse, solid is hollow. All solids are hollows. The only thing you get is the skin, and you don't even get the skin. What you get is an itinerary that goes throughout the whole cylinder, the whole whatever three-dimensional figure you're alluding to. Could be a cube, whatever, or a pyramid, cone, cylinder, any of those. But what is it? What you're doing really is moving a little location. We can't even say it's a dot. You're moving a location around and constructing it point by point. So that cylinder there, we all understand that in physics, it's a cylinder. It looks like my dough roller here, just the center of it, okay? Looks like that. That's a cylinder, okay? We got it. No, it doesn't get more complicated than that, okay? But that's not what a cylinder is for math, because they describe and define it as a bunch of locations, meaning that there's a location that's moving around and painting or constructing that cylinder. Okay? Again, I have nothing to show for that. What is a circle? Well, the same thing, but just to show, which also answers the questions of the previous two, the solid and the plane. A circle is a bunch of locations that are equidistant from a center. That's it. That's what a circle is. So a circle is not what you see there on the left. That's what they illustrate. And then some people say, well, it's just a ring. And if it's just a ring, what are we talking about? How thin is the ring? How wide is a location? Because that's what they've got. They've got a bunch of locations, and they say, well, the circle is just a ring. But see, the ring is nothing. It's a bunch of locations, which is what you see there. And I was kind enough to leave the different locations there so that you can see something. Otherwise, you would just see a dot going around. And that's what a circle is to a mathematician. It's not. It's distance traveled by a location, if that makes any sense to you. And a semicircle is the same thing, but half. It's half a circle. So the dot, or the location, travels and stops at the other side, half of the circle. That's what it is. You figure it out. See if that makes any sense to you. And what is a sphere? Since we're on the same road of circular geometries. Sphere is, you take that semicircle and you twirl it around. Both Euclid and modern mathematics define it in the same way. You twirl a circle, a semicircle around. So a sphere is not what you see there on the left. That's what they illustrate. That's what they show, and people say, oh, I understand that. That's not what a sphere is. Sphere is what you see on the right. Okay, and that's just the starting point. It just gets more complicated as you get to other geometries. Here are the other geometries, a little more complex maybe, some of them. Okay, and you start with a square, which is not complicated, but again, what is there to illustrate? Well, I don't know if you see that. There's a little dot going around, okay? It's on the far right underneath the green letters. So if you look carefully there, you'll see a little dots going around. And what it is, again, it's not even a perimeter. It's a location traveling around a perimeter. That's what a square is. That's how it's defined, and that's how it's described. But that's not what they show. What they show is that red thing that looks like a square there. For physics, that's a square. For math, that's what you get on the other side. This is what you order, that's what you get in the mail. Okay, what is a cube? Well, a cube is a bunch of frames, window frames. Okay, empty window frames. There's no window in it, just a frame. Okay, and we don't know how thick the frame is. I made them thick here so that you could see the frame. Okay, but in real life, the way mathematics describes and defines it, all you have is, again, just a little dot that you see there on the square, and that's just tracing a perimeter that is around a square, and then they build the cube with 6 of these. So that little dot has a lot of work to do, just going around this perimeter called a cube, and it's hollow, and it's got no windows. It's a frame without a window. Okay, so that's what a cube is in mathematics. Now that we're going to take that and we're going to build our tesseract with that. What is a tesseract? Well, they say it's a 4-dimensional object. But what you see there, it's a 3-dimensional pair of nested cubes, or that's more or less what it looks like, okay? That's more or less the idea. That's what you have objectively in front of you. Actually, you have 2 nested 3-dimensional cubes, one big, one small, and they're superimposed, okay, so that you can see the center one. They're transparent, so, again, so that you can see the center one. And both of them are superimposed on a 2D platform. So the notion here is that you have a 3D pair of cubes projected onto a 2D platform. That's what we have objectively up there, okay, in front of us. I don't care what they taught in high school. I don't care how they define or describe it. I'm saying that's what we have objectively in front of us. Hopefully you understand what objectively is. It means you're not going to interpret anything. You're just going to take what's in front of you. Okay? Now, what do they do next? Well, they say this is what we call a hypercube or a tesseract. And they have these cubes, and I don't know, they pull them out of the magic hat, the top hat. they wave their magic wand, they pull all these cubes out of there. And you say, well, where did all those cotton picking cubes come from? I mean, you know, this is 1,000 clowns coming out of Jack in a Box. That's all it is. There's no justification for this. And again, it's people who have a lot of, fancy stuff in their heads, you know, not science, but science fiction, lots of fiction in their heads. And so they see more than what's in there. Okay? They just say, oh yeah, we pull a box here, we pull another there, and there you have your hypercube. Well, you know, I mean, it has nothing to do with science or with physics. Okay, that's magic. That's all it is. What is a hypersphere? Again, the same as a hypercube, and they illustrate it like that. Like in this case, 3 nested spheres, transparent so that you can see the inner ones. What it is really a growing sphere. That's what that's the notion of the hypersphere, because you have to have time. And all these people say, no, you don't need time in any of these figures. Yeah, you need time in all of them. Absolutely all of them. Not one of these, because they're all built with motion. So not one of these so-called figures is a static figure. Not in mathematics. In the religion of mathematics, they're all built. They're all constructed. Constructed takes time and motion. All of these have time embodied in them, whether you like it or not. People look at the final product and say, well, that's a square, it's not moving, there's no time involved. That's a cube, there's no time involved. I can see the tesseract or hypercube, I can see the hypersphere there as well. It's like they see it and they say, see, that's a static image. But that's not what is conceptually defined or described by mathematics. When they define and describe, they get the ones on the right. They have motion and time embodied in all of these geometric figures. Until you understand that, you're just fooling yourself. They're showing you one thing, that's what you have in your mind. It's like you see the dot and you say, okay, I know what a point is. No, that's not the point. The dot is not the point. And likewise, when you see the line, no, the line is not the point. The line is not the line. You have a bunch of locations. You have an itinerary. You have motion. And this is all also built on motion. They're constructed with motion, meaning time. Okay? In fact, they tell you that the 4th dimension is time. And we'll get to that in a second here. Clarify that or build upon that. Okay, what is a torus? What's a donut? I like chocolate donuts, so I put a chocolate donut there. I hope you won't mind. Okay. Is that what they illustrate? Well, no, that's too simple and just makes you hungry. No, it's the one on the right that they like to show, the fancy one where the little dots roll around and they say, oh, look at a torus. That's neat. Well, if that's a torus, obviously it's got time and motion involved in it, embodied in them. You know, if that's a torus and it's twirling around, well, you got time. And that is what a torus is. A torus is the same thing as like a cube or a hypercube or a hypersphere. What you have is a little dot that's going around, not dot, it's really a location that's going around in different locations, moving through locations, right? And building your donut. And so when they show you the final product, you say, well, that's a donut. Yeah, but that's not what a torus is. A torus is something in motion. It is always in motion. All the so-called geometric figures of mathematics, right? None of them are figures at all. They are all dynamically built. They're constructed. They all embody motion. They all embody time, because otherwise mathematics would have no purpose for them. Mathematics cannot use any of the ones on the left. They have no use for a static figure. They have to move around because they're going to be measuring along the cube, the square, the donut. They're going to be measuring. They're interested in what their measuring tape reads. They're not interested in the object itself. Okay? So all geometric figures are built with motion and time. And he who doesn't understand that, well, has a mental problem, or he's got his religion very deep inside him. That's the only reason you're not letting go of that, because you're trying not to understand, because it's going to destroy your religion if you finally find out that there are no static geometric figures in all of mathematical physics. But that's what you got to come to grips with, because that is exactly the case. Okay, one site, because we got to show how this relates to space-time now. One fellow, he points to a site and he says, oh, but there's a new version of space-time. You know, you have the normal space-time that everybody visually sees out there, okay, which is the fishnet and a bowling ball, you know, on this canvas, on this trampoline, and then they roll the little marble and says, hey, it goes downwards, and that's what gravity is. And people have that notion, but some time back, someone came up with a different notion, because they said, well, I don't like that one. That's too surrealistic, because you're saying that the Earth weighs down space-time, and then you have this problem where the Earth has to use gravity to push space-time downwards. So this, what I call two-dimensional version of space-time, a lot of people don't like that. They say, well, that doesn't really give me an idea what gravity is. It's geometry, yeah, because you're bending space-time, but it's like, is that how things work out there in space? And so they've come up with a different version. And this fellow, he points me in the direction of a YouTube video that claims to be the originator, but obviously he's not, because 10 years earlier you can find the same version in someone else's YouTube. And so let me go with that. Let me show you what this file says. He says there's another version, update to the elastic sheet of space-time version. He points to that website there, to that YouTube site. And what is it? Well, here it is. Looks more or less like this. Okay, this fellow, you go in there, and this is what this fellow says. He says, he first goes through Newton, he covers that base. He says, free fall can be modeled by force, the force of gravity. He's referring to Newtonian force. In this case, not force equals mass times acceleration. He's really referring to force equals the constant g, gravitational constant g, times mass divided by distance squared. That's what he's referring to when he says force, okay? This force allows us to predict the movement of objects, stating that they are attracted to each other, two massive objects like the Earth. However, this description is merely an approximation. Well, yeah, a prediction is only a description. Without more, prediction is just description. You're just describing, for example, like I give the example always, that tomorrow at 2 o'clock there's going to be an eclipse. So far you haven't explained why. You just gave me a description. You said tomorrow there's going to be this thing that's going to happen. That's just the description. So far, you haven't explained anything. No mechanism, no anything. We don't know why an eclipse occurs. Okay, what triggers it to happen? And yeah, then he says this description, blah 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 blah. Yeah, because that's all he has so far. He has a description. Okay, when you use force, the word force from mathematics, all you're doing is describing. You haven't explained anything yet. Okay, and this is one of the big problems we have, because mathematicians don't understand the difference between an explanation and a description. This is going to be at the root of this whole problem. And so what does good old Einstein come up with in contrast to Mr. Newton? Well, he comes up with this, okay? Several 100 years later, 300 years later, he says, in 1915, Einstein proposed a new theory. This is the same fellow that puts this in his YouTube video. A rigorous mathematical model which made it possible to what? To describe again, okay? A theory, and he says describe. No, theories are explanations, not descriptions. Is possible, free fall more accurately. What does accuracy have to do with a theory? We're talking about an explanation. We're not talking about how accurate your mathematical equation or your measurement is. This is where we have a problem. These people don't understand the difference between a description and an explanation, and they call a description a theory. Okay, and this is a big problem. Big problem, because mathematicians have gotten used to using the word theory when there is not a single theory in all of mathematical physics. Mathematics can only describe, and descriptions are not theories. Theories are explanations. Okay, so we have to define these terms to find out what we're talking about. And this guy continues, says, for Einstein, there is no such thing as a force that would act at a distance. It is the fabric of the universe itself which gets distorted and drags objects into a fall. Well, there you see it. They put the bowling ball on the canvas, and the little ball, the golf ball goes around. So this is the two-dimensional version, what I call. You have the flat sheet, and then something bends it into the third dimension. Okay, that's essentially it. And then the little bowling ball, the little golf ball there just rolls around it, around the bowling ball. So what's the problem? The problem is this word fabric. Okay, so what is a fabric? What is that fabric? And they say that's space-time. Well, space-time is not a fabric, it's a concept. You might have doubts on space, but hopefully nobody has doubts on time. Okay, there is no physical object called time. And so this fellow is going to talk about, like every relativist out there, they're going to talk about bending and warping time. Very scary stuff. Okay, and here he goes. He says he's going to use this notion of geodesics that I covered in the past. And I'm going to use my two elephants. Okay, he uses ants, but it's the same notion. It says objects move in a straight line, but within a curved geometry. Okay, what they're saying is if the two elephants start out more or less, parallel, like in parallel, if you drew two tangents to the elephants, they would be in parallel. But as they move along the geodesics on a curved surface, they're going to meet. So these two parallel lines essentially meet at infinity, or in this case at the North Pole, so they're not parallel, okay? And what happens? Well, what they're saying, this is gravity. But again, this is not an explanation of how an elephant attracts another elephant. What they're saying is that as they move along geodesics, they get closer to each other. That's not a cause. That's not a mechanism. That's what the description saying, as they move along the geodesic, they end up at the same place. Okay? That's not a cause, a mechanism. The only way to produce a mechanism is to produce the physical objects that draws the two elephants together. Not saying that because they roll along geodesics, they get closer to each other. That's not gravity. Okay? But when he continues, he says, when they fall, objects move straight ahead. Where's straight ahead? Is your straight ahead the same as my straight ahead? But the curvature of space-time gives us the impression that these trajectories are deflected. Again, all these are descriptions. Not one of them is an explanation. We still don't understand what causes gravity, what causes this pencil to fall downwards to the floor. Okay, in this case, to my lap. Okay, so what does he have to do? Well, he has to introduce time, and this is where it gets dangerous, and which again confirms that all geometric figures, so-called figures of mathematical physics, involve time. Okay, and he's got to invoke time no matter what. Okay, here he is. He says the following. He says, space-time is an object with 4 dimensions. I don't know of any object that is 4-dimensional, but since an object is that which has shape, you're welcome to draw it. I need for you to draw a 4-dimensional object. Okay. Hopefully, if you can bring it to the conference, it would be even better. Okay, bring one to the conference, and we'll know that you've visualized, you've imagined your 4-dimensional object. 3 dimensions of space, but also one dimension of time. Which can equally bend and curve. Now, doesn't that strike you as odd? He's saying that time, there's a dimension called time, which we can bend and curve. Now, in physics, we can't even bend the dimension of length or of width or of height. I've never tried to bend a dimension. But this guy says not only time is the same thing as one of the other dimensions, but he can bend it. My God. Again, it just blows your mind away. What's going through the minds of these people? Faithfully rendering a 4-dimensional geometry is strictly impossible. No kidding. In fact, good old Stephen Hawking says, you cannot even imagine a 4-dimensional object or the 4th dimension. Yeah, nobody can. And so you have all these people out there who train you how to visualize a 4-dimensional object in steps. Like, it's not like you see it in one go, like you see, I don't know, a box or a sphere or whatever, a sphere meaning a ball or whatever. No, you got to learn how to see, how to visualize a 4-dimensional object. It takes training, they say. Yeah, you can't see it in one go. Okay, and here you have Mr. I know the same fellow. He clarifies, he says, time can flow differently depending on where we are. Flow differently? I didn't know time flowed. Time bends, warps, it flows. He's talking about a physical object. He's saying time is like a rock. It is the time component of the curvature which explains gravity. He's going to explain gravity, which is essentially what relativists do. He's going to explain gravity by using time. Now, I don't care what you do, but you can take seconds, minutes, hours, years, months, weeks, whatever unit of time you want. You cannot explain the cause of gravity with time, no matter what. You need objects. You can't do it with a concept. And this is what these people say. These people say they can explain gravity with time. And of course, if you're going to bend time and warp time and put mass and gravity on top of it or pull on it, yeah, I guess you can do anything you want, okay? Because it's irrational to begin with. The apple is moving in time. He's alluding more or less to Newton's apple. He showed the apple going on Newton's head, on going to the earth, why the apple falls, and now he's going to use that same apple under relativity. Okay, he says the apple is moving in time. In time? What do you mean in time? Is time a medium that you move through? In it? It progresses towards the future. Oh, which way is that? Please point to the future. Because you're pointing in my direction, but my future is in the opposite direction. I'm planning to go to the future in that direction, and your future comes towards me. So which way is the future? Please point to it. Show me that forward and future are directions. Okay? The curvature of space-time will gradually bend its trajectory between a temporal speed towards the future and a spatial speed towards the ground. So there's going to be like a trade-off there, okay? The apple moves in a straight line, but the curvature of space-time rotates the orientation of this straight line between time and space. The curvature of space-time generated by the Earth has merely converted this temporal speed into a spatial speed. They're going to switch dimensions here. They're going to turn the temporal dimension, the time dimension, and again they call it a dimension, they're going to turn it into a spatial dimension. To them it's all the same. And you say, well, this guy is probably not a degreed guy. Maybe he doesn't have a PhD or whatever. Now let's get someone who does. Let's get Mr. Stephen Hawking, who says exactly the same thing as this fellow. Okay? This is from his famous book, A Brief History of Time. He says an event is something that happens, and it's an occurrence at a particular point in space and at a particular time. So one can specify it by 4 numbers or coordinates. Okay, that's what a coordinate is to him, just a number. So one can, again, the choice of coordinates is arbitrary. One can use any 3 well-defined spatial coordinates and any measure of time. And here it goes. In relativity, there is no real distinction between the space and time coordinates, just as there is no real difference between any 2 space coordinates. First of all, good old Hawking, he had a PhD, I think. You would think he'd know better. He confuses coordinates with dimensions. To him, it's the same thing. And no, it ain't. They're not the same thing. Dimension are known as length, width, and height, and coordinates are known as latitude, altitude, and elevation, and altitude. So they're not the same thing. Coordinates point towards the object, and dimensions point away from them, because dimensions are the 3 mutually perpendicular directions in which an object may face or point. And coordinates is the location of it, has to do with the location of an object with respect to 3 reference points. And those 3 reference points have to be perpendicular to each other. So no, coordinates and dimensions are not the same thing, but he treats them as the same thing. He uses the word dimension, coordinate, back and forth alternatively, like if it didn't matter, casually. And so he says there's no difference between a time dimension and a coordinate or a dimension, a spatial dimension, meaning length, width, and height. He doesn't name them there, but that's what he's referring to. So mathematics, they have no differences between coordinates and dimensions, and they treat time as length and width and height. They don't see any difference. Why? Because they're not talking about dimensions or coordinates. They're talking about measurements and numbers. They're talking about units. They're talking about something they can put in an equation. That's why the dimensions of physics and coordinates of physics have nothing at all to do with the dimensions and coordinates of mathematics, which are not dimensions or coordinates. They're known as number lines. These people are talking about number lines and confusing them with the dimensions and coordinates of physics because they want to make sure that you understand that whatever math they do out there in Cambridge and Harvard has something to do with physics. For otherwise, their whole language of mathematics would be totally irrelevant. I mean, what are they doing all this math, all these equations for? Well, because they say, because this tells us something about the real world. When it doesn't, because the real world has to do with mechanisms. And these people are not giving you a mechanism. They claim they do, but then they give you the most irrational thing they can come up with, saying that time is warped. That time is a physical object that flows, that it's warped, that you can bend, that you can go through. They're treating it like a physical object, and at the end of the dissertation, they deny it. Oh, no, you weren't supposed to take it literally. You were supposed to pay attention to the numbers that we put there, the equations, not to take it literally like saying, did we warp time? No, of course we did not. But that's the mechanism that they give you. And they also dismiss that and saying, well, that's not important anyways, because that's philosophy. And so at the end of the show, you never understood anything. You don't know what they were talking about, because none of what they said matches what they illustrated. And so this fellow finally, after doing all that fancy footwork, this is what he says is the new version. It's not the one where you push down gravity. It's this 3-dimensional one where somehow this fishnet flows into objects that have mass. And supposedly all objects out there in space, they have mass. They weigh something. They're made of atoms. And so somehow it pulls this fishnet inwards. It's no longer a ball on canvas, which is what I showed a minute ago. No, now it's this canvas moving towards the center of the objects, of every object in the universe. And so because everything moves towards the center, and like assuming this is the Earth, so everything's moving towards the center of the Earth. Here you have the sun, everything's moving towards the center of the sun. Well, then that's where the pull comes in. They say, well, you have this fishnet going into the sun and another fishnet going into the center of the earth, and that's what pulls the earth to the sun. So we need to identify what this physical object that they're showing as a fishnet is. We need to identify what this is, because it's gonna move the earth. It's going to affect the sun. Both of these are physical objects. We can't see or touch this fishnet. Some people always say, oh, Bill, we can't see or touch your rope. Well, can you see or touch this fishnet that keeps the earth from flying out of the solar system? Can you see or touch this fishnet that is pulled, that pulls the earth towards the sun? And if you can't see or touch it, does it exist? Because that's the notion these people have of what an object is and what existence means. Well, does that fishnet exist? Okay, so those defenders of relativity, at least, they have a serious problem here because they're not identifying what that fishnet is. It's allegedly a physical object, but we can't see it or touch it around the Earth. Or so we thought, because then NASA sent gravity probe B up there and they said we touched time. We touched warped time. We were able to measure warped time because we touched it. The gyroscope moved, and we ascribe that motion to warped time. That's what NASA is telling you, literally. Okay, now this is not like they're using fancy footwork and fancy wording, figures of speech. No, they're saying that their gyroscopes measured the warpage of time. That's the conclusion of gravity probe B. That's what you paid all those tax dollars for. That's what they found out for you, thanks to your generous contribution. Okay. Sorry, got wrong. Did put that one up there. Okay, so here is the other version. Okay, so that I showed the version earlier. Now this is my criticism of this. Okay, let me pull this down. Okay, so the question is, what are those lines that make up this 3D fishnet? Because so far we see 3D, we don't see any 4D anywhere object, and so we need to identify what that 3D fishnet is, what it's made out of. What entity causes them to drift towards the Earth? I mean, what's pulling on that towards the center of the Earth? Why is it going in that direction? Why is that going in the opposite direction? Are objects physically attached to these lines? In other words, if the sun is attached to this fishnet and the Earth is attached to this fishnet, well, we can imagine, that the sun is being pulled by the Earth and the Earth by the sun. Right? There's a mutual attraction because they're both connected to the fishnet, and the fishnet is going towards the center of each one of these two celestial objects. We all can figure that out. The question is, what is this fishnet? Why can't we see or touch it? Okay, and again, you have to identify it. Is it a physical object? If not, what is it? Is it a concept? Okay, and so this is not a geometric theory, even in the best of cases. Okay, or even an explanation of a mechanism, because if that fishnet is made of time, as they say, and what you have is warped time, then you're not talking about geometric figure. What you're talking about is the flow of time. Time is somehow pushing or pulling objects because it flows. So what these people are saying, either time pulls or more likely pushes objects towards the center of the Earth because time is warped. There's a flow of time pushing on this pencil. That's what pushes it down. It's the warping of time. And because time flows, and they tell you that time flows, this object is being pushed by the flow of time. There is no other way to interpret that. And again, what they do is they turn time into a physical object in order to get their physical interpretation across. That's got to be understood by a rational person. Irrational people will never understand it. Okay, what really is space-time? Let's find out. Okay, here we have it. This is again from Mr. Hawking, Stephen Hawking. Event, a point in space-time, specified by its time and place. That's in his glossary. Space-time, the four-dimensional space whose points are events. Okay? So an event is a point in space-time, and space-time is a bunch of events, a bunch of points in space-time. And so what is an event? An event is something that, this is in the body of his book, Brief History of Time. An event is something that happens at a particular point in space and at a particular time. So one can specify with four numbers or coordinates a four-dimensional space called space-time. It is impossible to imagine a four-dimensional space. That's called the ether. Okay, that's what he's defined. If we're talking about points in space-time, and space-time is made of points, well, all they did was describe the ether, which is a bunch of particles that fill space. That's what ether is. Fills or is space, because they have two versions as well there. But there you have it. That's what good old Hawking defined. And you say, well, that's your interpretation, Bill. Now let's get someone with a little more power than Hawking. How about Mr. Einstein himself? Okay, here it is. This is what good old Einstein said, well, back in 1920. He says, we may say that according to the general theory of relativity, space is endowed with physical qualities. In this sense, therefore, there exists an ether. According to the general theory of relativity, space without ether is unthinkable. So yeah, the ether is a bunch of particles. That's what it is. In Einstein's version, it fills space. Other people say that space is the ether, is the bunch of particles, in which case they have to identify the medium or thing or whatever they want to call it that separates one particle from the other. We need to find out what that black stuff that separates two white particles is. Okay, and so that's where they're at. Okay, my conclusions on all of this. Very sad conclusions, okay? Conclusion, no figures in mathematics, okay? Geometry, there are no figures in there. No point, no line, none of those are figures. Okay? So we don't have figures. What we have is locations and itineraries. And so math phys is based on geometry, especially general relativity, and it's based on irrational foundations because we don't have a single object. Physics is done with objects and they don't have a single object. What they have is locations and itineraries. Okay? Space-time is alleged to be a geometric theory of gravity. Okay? That's what they claim, that's what they boast about. 2D space-time, which is space and time, you know, the flat canvas that where you're going to put the bowling ball, that's what we'll call 2D space-time, invokes Newtonian gravitational force. Something pulls that bowling ball downwards. It's known as gravity. And we have no problem understanding what they're showing because the bowling ball is pushing the canvas downwards. What they should do always, so that people get a shock, you know, and wake up, they should put it upside down because there is no direction in space, right? And so why don't they put the canvas upwards, right? And the bowling ball pushing the canvas upwards. Then people would say, hey, that's a little counterintuitive there. Then they would wake up to what these people are doing. Everybody can understand bowling ball on canvas going downwards. No one can understand bowling ball pushing the canvas upwards. That's where people would wake up and say, oh, hold it, that's counterintuitive. What do you mean the bowling ball pushes upwards? And what are you going to say? Well, it's gravity. Gravity always goes downwards. That's what they would tell you. But people are not aware. They're fooled by the images. Okay. Again, you know, all the images that they put out there have nothing to do with the mathematical descriptions or with their definitions. And so how about 3D space-time, which is the one going into the center of the Earth, you know, this flow of time into the center of the Earth? Well, time flowing and dragging objects towards the Earth's center, that also invokes force. Because you got to tell me what that time is. What is that object? Please identify that object. And it's got to be connected somehow. You know, it's got to be glued to the object to pull it, or then you have to push it. You know, you have to have time push it towards the center of the Earth. That's what these people are saying. Okay, and again, if that's the case, it's not a geometric explanation. What it is Newtonian force, because you're pushing, you know, the pencil towards the center of the Earth. In the best of you could also be pulling, you know, from the Earth, but that's usually not what they talk about. What they're saying is the time is flowing and pushing the pencil towards the center of the Earth. And so you got to identify that physical object they call time that you can warp, that is a medium, you know. It gets down to the word time. What do you mean by time? What is this physical object you call time? Is it, if it's an object, we can understand the mechanism. If it's a concept, all you're doing is describing. And then space-time is an irrational mathematical concept. Space-time, you put them together, you take nothing and a concept called nothing. Time is really, it involves memory. It's motion with memory, essentially. And so you take those two, you put them together, you make a physical object called space-time that you can warp, bend and warp and so on. Over my head. It is irrational to propose that mass or gravity can bend a concept such as time. And that is exactly what these people are saying. And what they say is, Bill, you're taking it too literally. You know, that was just an analogy. An analogy of what?